Swayam Prabha. Digital India. Educated India.
Okay, so let me use the same circuit that I was using last time. Which was this circuit with a number of resistors and a current source. I called this node N0, N1, N2 and N3, and the way I would go about doing nodal analysis is I make N0 my reference node. You could pick any one. In this case I have picked N0, and I write down the voltages of each node with respect to N0 as V1, V2, V3, and express all my relationships in terms of V1, V2 and V3. Okay. Now, so that means the voltage here is V1, voltage here is V2, and the voltage there is V3. And let me call this R11, R22, R33, R12, R1, R23 and R13. This is I1 and this is I3. Now in this case, what I first do is write KCL at nodes N1, N2 and N3. If I do that and I group together all the variables, I group together the coefficients of each of these variables V1, V2, V3, I get the equations in a certain form, and I can express that in a neat matrix form, which I am going to write down now. We saw that the diagonal elements of this matrix basically correspond to the total conductance connected to each node. Okay, so the first row corresponds to the KCL at N1, second row to N2 and third row to N3. And I will use the same ordering for the variables also. Okay, that is V1, V2 and V3. Okay, and the diagonal elements, this element A11 of the matrix corresponds to the total conductance connected to node 1, which is G11, the reciprocal of R11, G12 and G13. Similarly here, this element 22 will consist of G22, G12 and G23. Okay. And finally here in this position we have the total conductance at this node. And the off diagonal elements, this entry A12 for instance is the negative of the conductance between node 1 and node 2. So this is minus G12, and it's a symmetric matrix. This is also minus G12, and here we have the negative of the conductance between node 1 and 3, and here also the same thing. So this will be minus G13, and finally this will be, these two will be minus G23. Okay, and on the right hand side we will have the current sources, and in the first one we will have the current source connected to node 1. In the direction that it pumps current into the node. Okay, it's basically the total current coming into node 1, that is plus I1, and nothing is, no current source, independent current source is connected to node 2, so this will be 0. Finally here, and a current I3 is pushing current into node N3, so this will be I3. Okay. So this is what we had, and this is what, by solving this we get the node voltages, and this is what we call nodal, this is what is termed as nodal analysis. Okay. Now the circuit is not solved completely, but once you know all the node voltages, you know all the branch voltages. The branch voltages will be either the node voltage itself, for instance for this branch and this branch, the branch voltage equals V1, and if you take this branch for instance R12, the branch voltage is V1 minus V2. Okay, so that way you can find all the branch voltages, and you can also find the branch currents by using branch voltages and the element VI relationships. Okay. So this is what is known as nodal analysis. Okay, and as I said, these will be conductances, total conductance at the nodes, and these, the off diagonals ones, will be negative of the conductance between two nodes. Okay, so that's all that's there to it, and we get a nice symmetric matrix. Okay, now the only restriction is, in this case we have taken a circuit which has resistors and current sources only. We don't have other types of independent sources, that is a voltage source, or we don't have dependent sources yet. We will add them as we go along. Okay. So that's a quick review of what we did in the previous class. Any questions? Any confusion regarding that? Okay, and we have this equation in the form, the conductance matrix times the node voltage vector equals the vector of independent current sources. Okay, and this bar below the letter means that it's a vector, and finally this is the vector of independent sources. Okay, and to solve for this we have to invert the matrix and multiply by the independent sources. Okay, right now I will not worry about solving this. We will see examples of this later, but there are ways to invert the matrix. If it's a 2 by 2 matrix or a 3 by 3 matrix, you can do it by hand. Beyond that, you usually do it using a computer. Okay, but the point here is there is a systematic method of calculating all the node voltages. You first set up all the node equations, and then there is a procedure whereby you will get all of the node voltages. Okay. There is a question, why did I call this a matrix and this a vector? If you have a matrix with a single column, that's usually called a vector. Okay, a column, single column matrix is usually called a vector. So we have V1, V2, V3, which is, you can call it a 3 by 1 matrix, but it is common to call it a vector. Okay. Now, so like I said, I will not worry about solving this right now. It's assume that we will be somehow able to solve it. So what I will do now is to add other kinds of element which we have not added before. Okay. So let me take the same circuit and modify it slightly. Now let me remove this resistor R23 and connect an independent voltage source. Okay, and I will call this V0. Okay. So we want to do nodal analysis, similar analysis as we did before, but with independent voltage sources. Okay. So what I did was, I had a resistor here. I could have put a voltage source anywhere, even in parallel with it, but I have just removed that resistor and connected this voltage source. Okay. So now my question is, can we go ahead exactly as we did before? If not, what is the difficulty with this? Okay. The network connection broke and then something happened. Yeah, as some of you recognized, the problem is with writing KCL here and there where the voltage is connected. Okay. KCL is still valid. The current going here plus the current going there plus the current going there is 0. But the problem is, earlier when we had a resistor, we could express the current as this conductance times the voltage difference, V2 minus V3. Now we don't know what the current is through a voltage source. By definition, it will support any value of current. Okay. So that is the problem with doing nodal analysis when you have independent voltage sources. So now what do we have to do? So we have an extra unknown, let me call that Ix, and I will use the passive sign convention as always. I will show the current through the voltage source as going from plus to minus. Okay, that is, as we said, this Ix is not known. Okay, but I can still write the KCL at these three equations if I denote this as Ix, and that's what I will do. Okay, so at N1 I will write N1, the equation is exactly the same as before. Okay, so I will write it straight away. At N2, what we have are the currents flowing out, that is V2 times G22, V2 minus V1 times G12, and minus Ix. Ix is flowing in, so minus Ix is flowing out. And similarly at N3, what do we have? We have minus G13 times V1 and plus Ix, because Ix is flowing out of the node, and plus G13 plus G33 times V3, okay, equals I3. Okay, so we have an extra variable Ix. Now so we have the first equation is the same as before, and the second one and the third one have this extra variable Ix. So now I totally have 4 variables, V1, V2, V3 and Ix. Okay, and only 3 equations. So how do I go about solving this? Is there an equation I am missing? This is a question for the participants. I mean, I have now 4 variables and then only 3 equations. To solve for 4 variables, I need 4 equations, right? 4 independent equations. So where will I get the extra equation from? So clearly, so far I have not described the voltage source itself, and that gives me the extra equation. So this difference V3 minus V2 will be equal to V0. Okay. Let me write it with the same order. Minus V2 plus V3 equals V0. Some of you gave the answer that V2 minus V3 is V0. No, it is V3 minus V2 equals V0. Okay, with the polarity. So now I have 4 equations, that is the KCL at the 3 nodes plus the equation for the voltage source, and this is a system of 4 equations in 4 unknowns, and I will be able to solve this one. Okay. And I will write this in terms of the matrix. So what I have are for the case of nodal analysis with independent voltage source I have the variables to be the node voltages in general, n minus 1 node voltages plus currents through the voltage sources. In my circuit, I have a single voltage source, but let's say if I have L voltage sources, I will have L currents through the L voltage sources. So the number of variables increases by L. Okay, and the number of equations also increases by L because each voltage source provides a constraint. Okay. Okay. Now I will write out the equations in matrix form, including the extra variable Ix. This will be G11 plus G12 plus G13 and minus G12 minus G13, and if you look at the variable vector, it will be the node voltage V1, V2, V3 and Ix. Okay, and in the first equation for node N1, the variable Ix doesn't appear, so the coefficient here is 0. Okay, and in this case I will have minus G12 and here G22 plus G12. Okay, and here I don't have anything, and minus 1 because I have minus Ix. This is the KCL equation at node N2, and at node N3 I have minus G13. Okay, nothing for V2 and G13 plus G33, and I have plus 1 because plus Ix appears in the equation, and I have the constraint for the voltage source, which is that V3 minus V2, that is minus V2 plus V3, and these things don't appear, equal I1 0, I3. These are the currents into node 1 and node 3, and the last equation is minus V2 plus V3 equals V0. Okay, so this is the nodal analysis expressed in matrix form, and this has been modified to include an auxiliary variable, and that auxiliary variable is the current through an independent voltage source. Okay, and this scheme is known as modified nodal analysis. Okay, so whenever you have independent voltage sources, you need to have the current through the voltage source as extra variables, and then you will be able to again set up the equations systematically and solve for them. Okay, any questions about this? So the modification includes basically extra variable, which is the current through the voltage source. Okay, so any questions about this? How to deal with an independent voltage source in the circuit? When we have an independent voltage source, we define an auxiliary current, which is the current through the voltage source. So that gives us an extra variable. We get an extra equation from the equation for the voltage source. Okay. Now obviously if you have many voltage sources, the size of the vector will grow, but I have to emphasize here that the main point of doing this, that is being able to write the equation systematically, is so that you can solve it even for large circuits. Okay, it is not intended that you invert this matrix by hand. Okay, it is only through a computer, right? I mean, for any circuit of any reasonable size, you will need a computer to do that, but you have to set up your program so that it looks at the circuit and sets up the equations or this matrix equation correctly. Okay, and there are routines for inverting the matrix that you can utilize to solve this. Now this matrix, I will still continue to call it conductance matrix, but not all the elements are conductances. Clearly the ones in the last row and last column, they are not conductances. Okay. Now on the right side we have the vector of independent sources. It's not just independent current sources. Now we have independent current and voltage sources. Independent current and voltage sources. But otherwise the structure is exactly the same as before, which is the matrix G. As I said, I still continue to call it G, but not all elements in this are conductances. These are all conductances, but these are basically dimensionless. Okay, the last row and last column. G times V, that originally was the vector of node voltages, but now it also includes a current, and finally equals I. And again, this is a vector of independent variables. It has the current sources as well as the voltage source. Now I don't want to introduce a new notation, so I'm going to keep it as it is. Okay. Now, like I said, this is good for analyzing things with a computer, because the procedure is very systematic, right? For every voltage source, you simply add a new variable, which is the current through the voltage source, and also solve for it. And you add equations corresponding to each voltage source. Now, when you are solving it by hand, you would not want to increase the number of equations like this. Generally, you solve small circuits by hand, and then going from a 3x3 matrix to a 4x4 matrix is tremendously complicated. Okay, when you are doing hand calculations. Whereas a computer can handle matrices with thousands of rows and columns quite easily. Okay. So now for hand analysis, the nodal analysis is done with a very slight modification. Okay. So let me put down these equations again. So we introduce this extra variable Ix, right? Now what we do is, for instance, let's say I write up the equations like this, and the voltage source is connected between N2 and N3. Okay, so I add up the equations, KCL equations for N2 and N3. That is, I take this equation here plus that equation there, and I add them up to form a new equation.